We reached Pluto before we figured out how to go straight up. That sentence sounds wrong. Pluto is nearly 5 billion kilometers from Earth. Up is just up. You point a rocket at the sky and go. But that instinct is built on a misunderstanding of how the solar system actually works. And once you see the real picture, the fact that going up is harder than going to Pluto stops sounding absurd. It starts making perfect sense. The solar system does not fill space equally in every direction. The planets do not float at random heights and angles around the sun. They orbit inside a thin, flat disk called the ecliptic plane, left over from the rotating cloud of gas and dust that collapsed to form the solar system 4.6 billion years ago. Earth orbits inside that disk. Mars, Jupiter, Saturn, all of them. Almost every spacecraft ever launched has stayed inside it too. From the side, the solar system looks like a flattened disk full of activity. From above, it would look like a coin, a flat spinning structure with the sun at the center, and everything else moving in roughly the same horizontal band. That geometry explains almost everything about how we explore space, and it is why the regions directly above and below the sun have remained for most of human history almost completely unknown. Right now, you are moving at approximately 30 kilometers per second. That is Earth's orbital speed around the sun, fast enough to cross the moon's entire diameter in about 2 minutes. You do not feel it because everything around you is moving together. The ground, the air, the oceans, you. Every rocket launched from Earth inherits that speed entirely. A spacecraft leaving the launch pad does not start from zero. It begins moving sideways at 30 kilometers per second, locked into the same direction Earth has always been going. Mission planners do not fight this, they use it. Going to Mars, Jupiter, the outer solar system, all of it takes advantage of that inherited momentum. That is why spacecraft can cross billions of kilometers on modest amounts of fuel. But now try going upward instead, out of the disk, perpendicular to everything. Suddenly, that free speed becomes a problem. Those 30 kilometers per second are not pointing upward, they are pointing sideways. Imagine a car racing around a circular track at highway speed. If you wanted it to head off in a completely new direction, you couldn't just turn the wheel. At that speed, it would skid. You'd first have to cancel its sideways motion, then accelerate the new way. Spacecraft face the same problem, but worse. In space, there is nothing to grip, so the only option is to cancel that sideways motion and build new velocity upward. Mission designers measure this challenge in delta V, the total change in velocity a spacecraft must produce with its own engines. Reaching Mars requires roughly 3 to 4 kilometers per second of delta V, a small adjustment to an existing path. Reaching a truly high inclination above the ecliptic plane, say 90 degrees directly over the sun, requires canceling and replacing the full 30 kilometers per second of Earth's orbital speed. That is not an adjustment, that is starting over entirely. Going to Pluto requires less energy than climbing a fraction of that angle above the solar system. Distance was never the barrier, direction was. And because of that, one of the most scientifically important regions in our cosmic neighborhood has remained almost entirely unexplored. At this point, you might wonder, why does it matter? Why spend enormous effort reaching something that has no planet, no moon, no obvious destination? Because the space above and below the sun may control more of what happens in our solar system than almost anything we have studied so far. Think about how we observe the sun. Every observation in history has been made from inside the ecliptic plane, from Earth's surface, from orbiting telescopes, from spacecraft that stayed near the planetary disk. Every image of the sun ever taken before 2025 was taken from the side at roughly the same angle. That is equivalent to spending centuries studying Earth's climate while permanently confined to the equator. You would observe tropical patterns with great precision. You would miss polar circulation entirely. You would miss the mechanisms that drive the planet's weather as a whole. The sun's poles are not a peripheral detail. About every 11 years, the sun reaches the peak of its magnetic cycle. Its activity rises, reaches a maximum, then gradually falls before the cycle begins again. At solar maximum, something remarkable happens. The sun's magnetic north and south swap places. The polar magnetic fields weaken, briefly become disordered, then rebuild with the opposite polarity. Scientists believe the polar regions play a central role in that reversal, making them one of the most important places on the sun to observe. That cycle has consequences far beyond astronomy. At solar maximum, the sun produces more frequent and more intense coronal mass ejections, vast eruptions of plasma and magnetic fields that race across the solar system at millions of kilometers per hour. As they arrive at Earth, they interact with the planet's magnetic field. Strong events disrupt satellites, degrade GPS, interfere with communications, and in extreme cases, damage power infrastructure. The 1859 Carrington event, if it occurred today, could cause damage estimated in the trillions of dollars. The 1989 geomagnetic storm caused a 9-hour blackout across the entire province of Quebec. Predicting those events requires understanding the solar cycle. Understanding the solar cycle requires understanding the poles. Until quite recently, the poles had never been imaged at all, but that was only the first problem. The first mission to observe the sun from outside the ecliptic plane launched in 1990. Ulysses was a joint project between NASA and the European Space Agency. Reaching the polar regions directly was too expensive in fuel, so engineers designed a different route. Ulysses first flew outward to Jupiter, used the planet's enormous gravity as a slingshot, and bent its orbit roughly 80 degrees out of the ecliptic. For the first time, a spacecraft was flying over the sun rather than around it at the equator. What it found mattered. Ulysses measured the polar solar wind, streams of charged particles flowing outward from the poles at higher speeds and in cleaner, more organized patterns than the turbulent wind near the equator. The sun, it confirmed, behaves fundamentally differently at high latitudes than at low ones. But Ulysses carried no camera capable of imaging the poles directly. It measured the environment. It could not show it. That gap remained open for 3 decades. Solar Orbiter launched in February 2020 using repeated gravity assists from Venus to slowly tilt its orbit further from the ecliptic. Each flyby climbed a little higher. The process took years. In 2025, Solar Orbiter reached approximately 17 degrees relative to the ecliptic. 17 degrees does not sound impressive until you realize nobody had ever photographed the sun from even that angle before. And the images that came back did not show the calm, organized polar field that models had predicted. They showed turbulence. Magnetic fields of opposite polarity were interleaved in unstable patches. The poles were actively churning, caught in the middle of the sun's magnetic reversal at solar maximum. It was the first look at the machinery driving the solar cycle. But 17 degrees is still a long way from looking straight down. And the closer scientists looked, the stranger things got. Surrounding the entire solar system is a structure called the heliosphere, a vast bubble of charged particles generated by the solar wind, extending far beyond the planets in every direction. Every spacecraft ever launched, every planet, every living thing we know of exists inside this bubble. It is the solar system's protective shield against the harsher radiation of interstellar space. For decades, everyone assumed they already knew its shape. Textbooks showed it as comet-shaped, a rounded nose at the front, a long tail trailing behind. That model was based on the physics of how the solar wind pushes against the incoming interstellar medium. Turns out, we probably had it wrong. More recent models, informed by data from the Voyager spacecraft and missions that map the heliosphere's boundary, suggest the heliosphere may not resemble a long-tailed comet, after all. Some instead propose a different shape, with two looping jets rather than one long tail. The interstellar magnetic field appears to squeeze and reshape the bubble in ways that earlier models did not predict. Neither version has been confirmed, because every measurement has come from inside the ecliptic plane. Voyager 1 and Voyager 2, the only probes to cross into interstellar space, measured the heliosphere's boundary at just 2 locations. 2 data points on a structure spanning hundreds of billions of kilometers in every direction. To know the true shape of the bubble that contains all of human history, we may need spacecraft that climb above it and look back down. Not sideways, from above. So, how do you actually get there? At first, the answer seems obvious. Build a bigger rocket, carry more fuel, push harder. But once engineers run the numbers, that approach collapses. The energy required to cancel Earth's orbital speed makes brute force essentially impossible with any currently foreseeable propellant technology. That's when a completely different idea starts to make sense. Imagine diving toward the one thing you are trying to escape from. Every instinct says, pull away. Engineers decided to do the opposite. They aimed directly at the sun. This concept is called the solar Oberth maneuver. When a spacecraft falls toward the sun, solar gravity accelerates it to extraordinary speeds. The closer it gets, the faster it moves. At the very closest point of the approach, moving faster than at any other moment in the mission, the engines fire. Same fuel, completely different result. This burn performed at that speed, deep inside the sun's gravity well, generates far more orbital energy than the same burn would produce anywhere else. The dive becomes the launch. Falling inward becomes the mechanism for escaping the plane that trapped every mission before it. The Parker Solar Probe has already reached within approximately 9 solar radii of the sun's surface, close enough that this kind of maneuver is beginning to move from theoretical to potentially practical. But not every solution needs to be dramatic. There is a quieter path. A solar sail uses an enormous reflective surface, potentially thousands of square meters, and lets sunlight itself do the pushing. No engine, no fuel, just photons pressing gently against a mirror for months, then years. In the frictionless environment of space, that patience accumulates into real velocity. A sail mission, spiraling slowly inward and gradually tilting its orbit, could climb above the ecliptic over years of continuous gentle thrust, reaching inclinations that chemical rockets cannot achieve at reasonable cost. One approach dives toward the sun and fires at the last possible second. The other rides sunlight for years without burning a drop of fuel. Both are being studied. Neither has been approved. And if you were designing the first mission, the one that finally looks straight down at the sun's poles and maps the true shape of the heliosphere, which would you choose? If either mission succeeds, what it sees will be unlike anything captured before. From directly above the solar system, the ecliptic plane would appear as a luminous disk, lit faintly by billions of years of dust from comets and collisions, the same dust that creates the zodiacal light visible from dark locations on Earth. The planets would be points tracing a flat pattern against the darker space above and below. The sun's poles would be visible in direct overhead imaging for the first time. The magnetic field structure, the fast polar wind, the dynamics of the solar cycle exposed from an angle that every previous observation was geometrically unable to reach. The heliosphere's boundary could be mapped from outside the disk. Its true shape the shape of the bubble that contains all of human history, measured rather than modeled. That is not a refinement of existing knowledge. That is a foundational question about the structure of the place we live. The solar system's flat geometry is so familiar, it has become invisible. Every mission, every image, every trajectory operates within the disk, as though it were the only available space. For most purposes, it is. The planets are there, the targets are there, and Earth's inherited velocity makes travel within the plane achievable. But the disk is not the solar system. It is the inhabited part of the solar system. Above and below it, the sun's poles remain largely unobserved. The heliosphere extends in 3 dimensions, sampled along only a thin slice. The engine of the solar cycle, the mechanism that drives space weather, geomagnetic storms, and the conditions that allow or threaten life on Earth, operates at latitudes humanity has barely reached. Our spacecraft have crossed into interstellar space. The sun's own poles have never truly been seen from straight above. We crossed billions of kilometers to Pluto. The greatest unexplored direction was directly above our heads the entire time.